Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Bom dia, Brazil. I'm very happy to welcome my mathematical brother, EXEL, from Florianópolis, who will tell us how flows flow on uniform row algebras. It's all yours. Take it away.
Thank you very much, Piotr. It's a great pleasure for me to be speaking in this seminar. And so my title is, as you see, Flows on Uniform Row Algebras. And that's based on a joint work with Alcides Bus from Florianópolis and Bruno Braga from IMPA. So let me begin by introducing the object of interest. Actually, the object of interest is a metric space, but we're going to look at metric spaces from a slightly different point of view. And the main notion involved in here is the notion of a coarse function. So if x and y are metric spaces, then a coarse function from x to y is a function that satisfies this inequality over here. So that the function, the distance between 2 points, the image of 2 points is somehow bounded based on the distance of the points themselves, right? So the idea here is that the function does not spread points too far apart. So obviously, any Lipschitz function is coarse, right? An example of a function which is not coarse is the function from the natural numbers to itself sending n to n squared. And the reason is that if you look at points n and n plus 1, the distance is 1. But if you look at the distance between their images, the distance is 2n plus 1. So points at distance 1 start getting spread out apart. So we don't like that. So that function is not coarse, right? Now, it should be pointed out that this function is continuous. So coarseness doesn't have anything to do with continuity. So here's another function, the rounding function, the function that rounds a real number to the nearest integer number. This function is coarse, but it's discontinuous.
Yes.
Okay. So another example is any bounded function is coarse, no matter what, because that supremum over here is going to be finite for every x and y. So once we understand what a coarse function is, we should think about the notion of coarsely equivalent metric spaces. So two metric spaces, x and y, are coarsely equivalent if we can find functions between them, f from x to y and g from y to z to x, such that the compositions in either direction are near the identity function. So what does this wiggle here mean? It means that the distance between the composition of g and f to the identity function is finite, and likewise fg is close to y in the sense that the functions have a finite distance in the sense of a supremum of the distances. Okay, so here are examples.
I have a question. My question is about this equivalence relation. So the only equivalence which is used in this definition is the equivalence between the compositions G composed with F and F composed with G and identities. What if we replace this by equivalence relation with the supremum of the distance between images of two maps, arbitrary two maps, is finite?
I mean, we usually say that two maps are close if the distance is finite. Right? So I'm using this notion of equivalence of functions in order to define the notion of coarse equivalence, right? So coarsely equivalent means that you can find those two functions such that compositions are close to the corresponding identities. Okay? So here are some examples of coarsely equivalent spaces. The integers and the real line, they are coarsely equivalent because you can find those two functions over here. So the identity function from the integers to the real line, and going back, the truncation or the round function that we were talking about, right? So it's easy to see that those two functions obey the definition in the sense that, I mean, in one composition is already the identity. The other composition maps a real number to a nearby integer number, so the supremum is finite. So likewise, the power set Zn is coarsely equivalent to Rn. And here's a question. Do you think that Z and N are coarsely equivalent? So the answer is no. I mean, those are two metric spaces which are both discrete, and therefore they are homeomorphic, but they are not coarsely equivalent. You may think of that as an exercise to show that they are not. The idea is that, go ahead.
I have a question to this example number C. Can we imagine that coarsely speaking, this Z looks from afar like a line?
That's
exactly. And looks like a semi-line.
That's exactly the comment I was about to make. So the notion of coarse equivalence is that when you step back and you look at those spaces from a distance, they look like, and exactly the integers look like a real line, but the natural numbers look like a half a line. So that's exactly the point that this notion of coarse equivalence is supposed to make. Likewise, Z cross Z is not coarsely equivalent to Z because one of them looks like a plane and the other one looks like a line. If we think about bounded metric spaces, any bounded metric space, if you look at a bounded metric space from a very long distance, it's just a point. So all bounded metric spaces are coarsely equivalent to any other bounded metric space. Okay. So given that, so I mean, so far what I told you is not really very meaningful for the results that I am planning to present today, but I just want to give an idea of how are we supposed to be looking at metric spaces, right? So we are not interested in homeomorphism. We are interested in the point of view of a metric space which is invariant under coarse equivalence. So first of all, we're going to restrict ourselves to what's called ULF spaces, meaning uniformly locally finite spaces. So a metric space is uniformly locally finite. If you look at the ball, at the balls in your space, if you fix R and you look at all balls are supposed to be finite. So the number of elements in every ball is finite, and they're not only finite, but they are uniformly finite in the sense the supremum of all balls of the same radius are finite. So in that case, it's easy to see that the spaces must be countable and the metric topology is discrete. So as we already mentioned, the goal is not to study local phenomena, but to focus on the large scale geometry of our space X.
May I have a question at this point?
Okay.
In this uniform local finiteness, we are using balls of some radius, and this radius is a parameter here.
Exactly.
What if these balls are replaced by some other local shapes?
There is a notion of a uniformly locally finite metric space, which looks a little bit like the definition of a uniform space. In topology, there's a notion of a uniformity of a space, which is the situation where you can define uniformly continuous functions in topology. So it's a generalization of this notion, which does not require you to deal with balls, but that's another story. But you're right in the sense that the generalizations of this notion are studied.
Mm-hmm. But
okay.
Is this equivalent in this case?
It's more general. It's more general than this formulation. Yeah.
So this is more special.
Yeah. Oh, okay. So what are examples of uniformly locally finite spaces? The natural numbers, the integer numbers, and one of the most important examples is the examples of finitely generated groups. So if you fix a finitely generated group and you fix a generator set, and to make it simple, I'm going to assume that the generator set is symmetric in that sense, then we can define the length of an element in the group to be the smallest number n, such that your group element can be written as a product of n elements in G. So with the length function, you define a metric, the distance between G and H, to be the length of GH inverse. So that length is a uniformly locally finite metric on the group, and it's easy to see that the ball of radius n around the group element has at most this number of elements, the nth power of the size of the generator set. So that's a very, very important example, and this is crucial in the study of geometric group theory and so on. Okay.
Sorry, may I have another question?
Okay.
So this metric is even more than homogeneous or locally homogeneous, because it's a right invariant metric.
Yes. I mean, the left invariant.
But on the group, we have also left translations.
The left invariant metric is also an example, but you get a space that's coarsely equivalent with the original one via the function G going to G inverse. So you don't get anything new, right? Pretty soon we're gonna see why did I choose that metric in order to speak about partial translations. But okay, so here is the main actor in this whole business, the row algebra of a uniformly locally finite space. So we're now fixing your left space X, and this whole business started in 1988 with John Rowe's definition of the uniform row algebra denoted C star U of X, which is a C star algebra that captures the large-scale geometry of X in C star algebraic terms. So these algebras, they were introduced to study the index theory of elliptic operators on non-compact manifolds, and is also related to the Korsabaum-Kohn conjecture and the Novikov conjectures. Recently, mathematical physicists have started using uniform row algebras in the study of topological insulators. And last week, I saw a paper by Kitzius, Schick, and Vigolo with this intriguing title, The Failure of Surjectivity in Odd Degree. So that I haven't really dived into this paper, but I suppose it might be very interesting in related to the Korsabaum-Kohn conjecture.
Sorry, okay, but what is a warped cone? What is a warped cone?
I believe it's an example of a coarse space, but as I said, I have not yet read the paper, And so it seems to me, by reading the abstract, that it is a counterexample to Baum-Cohn. And the curious thing is that people have suspected the Baum-Cohn to fail in even degree, and apparently they have shown that it fails in odd degree. So that's even more intriguing. But we're not here to talk about Baum-Cohn.
Sorry if I may interrupt for a moment. I believe that the name comes from the fact that somehow this is some kind of metric space in which one can define something which is like a shortcut. And this name, warp cones, resembles somehow the situation where you are talking about the so-called warp drive, where in science fiction books, where you so probably maybe it could be the reason for calling it in such a strange manner.
Okay, all right. Thank you very much. So let's.
May I comment on this?
Yeah.
So forgetting about science fiction, so the notion of a warp metric is related to the fact that something is not of product type. This usual use of the word. Okay, so if you think about a cylinder, so the cylinder is like a product metric structure. So cone is an analog of a cylinder when one point is identified. Okay, with an identification of the circle at infinity with a point. Okay, so probably this warped cone is in the sense that it is not linearly trivial cone over something, but the metric on this cone is deformed. In the same sense as if you deform the structure of a Cartesian product, you obtain something which is a bundle. So the same you can apply to the construction of a cone over something, over some base. You can deform it to make it not of usual cone structure, but with a metric a little bit deformed.
Okay.
It's my suspicion. It's the usual meaning of the word warp in Riemannian geometry.
Okay.
It's, I'm just browsing through the internet, and this concept of warped cone seems to be very well established in the literature. It's just that I cannot find the definition, but it is something very standard. I mean, you have a title: warped cones, non-rigidity, and piecewise property.
I should say that this notion is really not the direction that we're going here.
Okay.
So it's certainly interesting to think about it later, but I just brought it because it seems to be an interesting breakthrough in this course Baum-Cohn conjecture. Okay,
but it appears in the same paper as Gurian's U property A, which was in your abstract.
Okay, it's gonna pop up very soon, and it pops up everywhere. Every time you talk about row algebras, use paper is fundamental. Okay, so a partial translation on a ULF space is by definition a function f between two subsets of x, any two subsets of x. So we're looking at a bijection between subsets of x, satisfying this property down here. So this means that the f is close to the identity function on A, right? We have already touched upon the question of when two functions are close. So this property here says that f is close to the identity. So a partial translation is any bijection between sets which is close to the identity map. So in the finitely generated group case, we can speak about translations, right? On a group, we can speak about translations. And every translation is a partial translation, because if you compute the distance between the translated point gx to x, this is what you get, and x cancels. And so the distance is constant. It's not only bounded, but it's constant, right? So this notion of translation is exactly what inspired the notion of a partial translation on a space. Any partially defined bijection that moves points close to the original point you started with. So once you have a partial translation,
can I ask a question?
Yes.
Yeah, go ahead.
Dabrowski. In this definition, any set should be a set, because it looks like a family of bijections. You need a family for any A and B set, which is too strong. I think A set for you fix A and B, and for this pair you define.
Exactly.
Correct?
Exactly.
Okay.
Exactly.
Thanks.
That's what I'm talking
Thanks.
about. Yeah.
Okay, thanks.
I mean, I drew my point in writing the word any here is that I'm not worried about restricting sets to any kind of special.
Okay, thanks.
Okay, so now once we have a partial translation F, we are going to define a partial isometric operator on the space L2 of X. So X is here seen as just an index set, and with that you define a Hilbert space of square summable functions on X, and this Hilbert space is going to be central in everything that's going to happen from now on. So beginning with those operators that I'm calling VF, and I'm defining them on the canonical basis of L2 of X, which I denote by delta X. So VF is the operator that sends each delta X to delta F of X if F of X makes sense, that is, if X is in the domain of F, and if I cannot define F of X, then I simply map this basis vector to 0. Okay, so this is easily seen to be a partially isometric operator. I mean, in the sense that this is only defined on the basis, so we have to extend it linearly to the whole space, but it leads to a partially isometric operator on the Hilbert space. One case which is
a question.
There is a question.
Sure.
I have a question to this previous definition of this motivation for this translation map. So, could you come back half a page? Yes. So, this condition about the supremum, this is a coarse condition. But being a bijection is not a coarse condition. So,
yes,
speaking about the motivation for this notion in this coarse geometry, why people do not think about things which are bijections, for instance, up to some coarse equivalence? Because being a bijection is not it's a notion which is not invariant with respect to this coarse equivalence of maps.
I think you would have to ask John Rowe that question, because that's the definition given by Rowe, and I'm pretty sure that this is open to generalizations, and maybe you can generalize it in that way, but that's the gadget that we have been studying.
And I think that maybe this notion of this, how it is called, locally uniformly bounded, yes, it implies being discrete, so everything is countable. So once you have countable sets, being bijection is just being in. Everything is modeled on something which is discrete, so maybe it is not such a strong assumption.
Yeah. I mean, we might get into trouble in defining the operators that we're talking about. I'm realizing that the sound coming from Poland is the only sound that seems to be imperfect for me. I wonder if you have any problem in your microphone. Because I'm having trouble understanding the sound coming from Poland, but I can manage. Okay, so let's talk about a special case of partial translation. If you choose any set A and look at the identity function on A, that's a special case of a partial translation, right? And VF, what is VF? It's certainly going to be the orthogonal projection on L2 of A. So those are trivial examples of partial translations, which at the same time are very important in the theory. So here's a definition of what is the uniform row algebra, the C star uniform row algebra of X. C star of U is the notation. That's the C star algebra of operators on L2 of X generated by all of those VFs, right? So that's the definition. That's not the only definition. I'm going to show you another definition soon, but it's a very clean definition in my opinion, right? So of course, if you have all of the VFs there, you also have the V for the identity function, and it's not hard to show that the all of those V sub-identity of A, which are actually the projections onto L2 spaces, right, for subsets, the linear span, the closed linear span of those VFs will give you all diagonal operators on the Hilbert space.
Maybe just a quick question. Wouldn't be enough to take for A just one-point subsets, all possible one-point singletons?
No, because if you do that, you are not going to get L infinity, you will get C0.
Ah, I see. Okay.
Right.
Yeah, of course.
Yeah, you would only get compact operators for instance.
Sure. It is norm limit. Yeah.
So the algebra of diagonal operators is isomorphic to L infinity of X. And so we should realize that L infinity of X is a subset of our algebra. And as a consequence, the uniform row algebra is not separable. Okay, so there's lots of results in C-star algebras which require the algebra to be separable. So we are simply saying bye-bye to those results and facing this beast by ourselves. So here's a little intermission for people who like inverse semigroups like I do. So if you have any set, the notation I of X...
Sorry, what is this word for inverse semigroup and what?
Aficionados. So for people who like inverse semigroups.
Okay.
Right?
Fans of inverse semigroups.
Yeah, fans of inverse semigroups, yeah. I mean, some of my co-authors who have already seen my slides, they complained about it, but I mean, at least I have been educated in California. In California, everybody knows what aficionados mean because of the big Spanish influence over there. Okay, sorry, that's just a joke. Now, if, as I was saying right now, the I of X, by definition, is the set of all partial bijections on a set X. No restriction related to metric and all that, so that's a very important inverse semigroup. And if X is now our ULF space, we can look at a subgroup, a sub-semigroup, which I'm denoting PT of X, which are the partial translations. So what this whole discussion leads to is that the partial translations, they form an inverse semigroup. So here's a question. If you know this inverse semigroup, if you just know the inverse semigroup multiplication, can you recover the uniform row algebra in terms of this inverse semigroup? Like, I mean, people working in inverse semigroup, they define the inverse the uniform C-star algebra of an inverse semigroup. That's in Patterson's book. That's an important example in Patterson's book. So is the uniform row algebra isomorphic to the universal C-star algebra of this inverse semigroup? would anybody like to take a guess in that direction?
Sorry, but before guessing, I have two things. I mean, one, to close this issue, I just double checked on Webster. Aficionado is an official English word. So Adam, you have no right to complain. I know it comes from Spanish, but it is in Webster, so it's an official English word. When you try Google Translate, aficionado is translated into aficionado.
I don't complain. I just don't know this word.
Yeah, it's miłośnicy in Polish. Okay.
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 But now more to the subject matter. Would you mind very briefly reminding me what is an inverse semigroup? I have heard the definition from Gilles a million times, but I forgot. Just in one sentence.
So an inverse semigroup is a semigroup that is a set with a single associative operator, such that for every x there exists an element x star, such that x star is equal to x, and x star is equal to x star.
Okay.
Right.
Okay.
It's exactly the equation that defines a partial isometry.
Yeah.
And okay, so I mean, I am aware that I am veering off topic, but since I am very much into inverse semigroups, I realize that this is a connection with uniform row algebras. So the answer is no. And also, questions like this almost never have yes for an answer. For instance, the Kuntz algebra contains an inverse semigroup that generates it, but the Kuntz algebra is not the universal C-star algebra of the inverse semigroup. The answer is that the universal row algebra is the tight C-star algebra of this inverse semigroup. So this is just an occasion for me to make to advertise this notion of tight C-star algebra of inverse semigroups, which I like very much. But I mean, if you're not into inverse semigroups, if you're not an aficionado, then you can simply ignore it. Okay.
So now I have to ask you, what is this C-star tight?
Yeah, it's a whole other topic, and it wouldn't it would take a lot of time for the definition of the C-star, the tight C-star algebra. But it's an interesting theory, which I like very much. Okay, so here's another definition of the uniform row algebra. So let's take a bounded operator T on our space L2 of X, and let's define the propagation of our operator. So the propagation of T is this. I take all of this, these are the matrix entries of the operator. I look at all of the non-zero entries of the matrix of T, and for those, I compute the distance from X to Y, or X and Y are the indices of the basis vectors, right? So if this supremum is finite, I will be interested in this operator, and I'm going to call this an operator of finite propagation, right? So the idea is that a finite propagation operator has a matrix that lives on a bounded band around the diagonal of our matrix, right? So this is the definition of a finite propagation. An example you can take as an exercise to show that if F is a partial translation, then this operator VF we've been talking about is a matrix of finite propagation. An interesting remark about those operators is that if you're given a matrix, an arbitrary matrix, and I ask you, is this the matrix of a bounded operator? This is a very difficult question it's very hard to tell from the entries of the matrix whether this is a matrix of a bounded operator. But if the matrix has finite propagation, then the answer is this is the matrix of a bounded operator, even only if the supremum of the entries is finite. So this makes the study of operators based on the entries something very important. It's easy to see that the set of all finite propagate operators, which I'm going to denote C star U brackets X, this is a star algebra of operators, not a C star algebra, but the closure of this guy within the bounded operators is precisely C star of U of X. So C star U of X is the closure of the set of finite propagation operators. And in fact, it's my impression that John Rowe's definition is more along those lines.
Sorry, may I have a quick question?
Yeah.
Why it is called C star U? U stands for universal?
Because there's another one. There's another one, and which I mean, I myself have questioned this definition the first time I read it, and I don't think I have a good reason for that notation, but it's standard across the theory.
But is it true, for example, for this that you have a canonical epimorphism from this C star U to the other version?
No, it's not along these lines. It's not along this line.
Okay, there is a comment on the chat that.
U is for uniform.
Uniform. Okay, for uniform. Okay, thank you.
Exactly. It's called the uniform row algebra, not the. I mean, the row also define the row algebra, which has a very similar definition, but it's where we have what's it called scalars. There are matrices where the entries are compact operators, but that's a totally other story. So let's now go into.
I have a question. I have a question. Coming back to this definition of this finite propagation, could you show this matrix again?
What would you like to
put on the diagonal? Yeah. So this is the matrix representing an operator on L2.
Yes.
In the standard Hilbert basis of small L2.
Exactly.
Okay. So the shape of this matrix depends on the choice of this standard basis. My question is, what about taking another basis, Hilbert basis of L2? And then be this property characterized intrinsically?
There's absolutely nothing you can say if you look at other bases. And I should say that the study of row algebras is very much connected to this particular basis. So there's no sort of invariance that you can look at. So
even if you do something with this basis, which comes from, for instance, from partial translations or something like this, you can destroy this special structure of this matrix.
Yes. Yes.
Okay.
You can.
Okay. Thank you.
In a certain sense, we're going to be talking about conjugation of row algebras. So your question might be partly answered later, but I mean, the point of view is that uniform row algebras are studied from the point of view of this basis, right? So I mean, it's a little bit like for Neumann algebras. For Neumann algebras can be abstractly defined, but they are often studied in relation to the Hilbert space where they are represented. And so here we are not only focusing on the Hilbert space, but also on the basis of that Hilbert space. Now let's talk about flows, which is the main topic of the talk. So choose a function h from x to r, any function, and look at the diagonal operator. Look at the diagonal matrix having the values of this function along the diagonal, and regardless of whether or not this function is bounded, this always defines a self-adjoint operator on the Hilbert space, which is could certainly be unbounded and therefore densely defined. Every choice of entries along the diagonal of a matrix defines a self-adjoint operator on L2 of x. The notation for the function is h, but I am also going to define, to denote by h the corresponding operator. So this is an operator on L2 of h, which is L2 of h is not the domain of the operator, but it's customary to say that h is an operator on L2 of h when its domain is a dense subset of L2 of h. So since this is a self-adjoint operator, it generates a one-parameter group of unitary operators, which I'm denoting here UT, simply the exponential of this operator. And given this unitary operator, we can define an automorphism of the whole algebra of bounded operators simply by conjugation, right? Now, what happens if we conjugate an operator T by this unitary, by looking from the point of view of the matrix of T? So if this is the matrix of the operator T, what would the matrix of the conjugated operator be? Here is what you get. You get an easy form because you're conjugating by a diagonal operator. And it turns out that all you're doing is multiplying the coefficients in the matrix by some coefficients. So an important observation is that this matrix and this matrix, they share the positions of the entries which are 0, right? So if this matrix over here is a finite propagation, this is also going to be a finite propagation. So by going to limits, it's easy to show that this automorphism leaves the uniform row algebra invariant, right? And so if we have an automorphism, we can define what's called a one-parameter group of automorphisms by this. So a one-parameter group of automorphisms, by definition, is simply a homomorphism from the real line to the group of automorphisms of our C-star algebra. So I am also going to call this a preflow. A preflow is the same as a one-parameter group of automorphisms. Now, the trouble is that this guy here is not strongly continuous. So by a flow, I am going to call a preflow on a C-star algebra that is strongly continuous, meaning that this function here is continuous for every element in A. That's a very important notion in group actions, right? The notion of strong continuity. So what we see is that our sigma H is always a preflow, but there's nothing you can do with preflows. I mean, all of the interesting examples occurring in applications are flows, and all of the theory about group actions requires strong continuity. So we would like our preflow to be a flow. The answer is easy. The preflow sigma H defined up here is a flow even only if H is a coarse function. Remember the definition of a coarse function. A coarse function is the supremum of the distance of f of x to f of y is finite if x and y have a bounded distance.
So you're using the standard metric on a real line, yes? Euclidean metric, yes?
Yes, exactly. Yeah, the coarse functions are functions between metric spaces. So h up here, somewhere up here, h is a function from x to r. So I'm seeing those two X and R as being metric spaces. So this is coarse.
Can I ask a question?
Sure.
So if I remember, in the usual case of operators on a Hilbert space, if you have a self-restricted, I mean, the rule is self-adjoint operator, then it exponential generates a strongly continuous group of unitaries, strongly continuity. So
no.
What is the problem here?
No, I mean, if H is bounded, then the exponential group is continuous. But if H is unbounded, then the unitary group is continuous in the weak operator topology.
Okay.
So, I mean, of course, we are very much interested in the case of unbounded operators. Okay. So, from now on, flows that come from coarse functions will be called diagonal flows. Diagonal flows are very central in this case. So let me, at the beginning, I thought that I was going to finish early, but I can see that time is running fast. So I'm simply going to skip the business of KMS states, and let's go straight to the main point, which is classification of flows.
Rui, I mean, you still have 44 minutes, and as long as you finish before we see the smoke from the Sistine Chapel, it's fine.
Okay, so let's say at the end, I can come back to the business of KMS states, if you remind me, if we have enough time.
Exactly.
So our goal is to classify flows. So the question is, what are all flows on our system? That's the bold question that I'm asking. Tell me what are all flows on this algebra. So the justification is related to KMS states, so that's going to come later. Mm-hmm. So the first point is that if you have a flow, if sigma is any given flow, then there always is a self-adjoint operator H on L2 of X. And from now on, self-adjoint is always going to be possibly unbounded, densely defined self-adjoint operator, right? So any flow, whatever, it's always implemented by a self-adjoint operator H. That's a very physical statement because H is often associated to the Hamiltonian, to the energy of the system. So every flow.
I have a question. Maybe my question would be one of these questions listed below. So maybe I will hesitate to ask it. I don't know. My question is the following: whether the statement of this theorem is the same as saying as every flow is unitarily implemented, but not necessarily by e to the power ith for some self-adjoint. Probably it's the same due to the Stone theorem, but I'm not sure.
The Stone theorem, there's a catch in the Stone's theorem because there may be cocycles involved. And proving this is a little bit related to dealing with proving that a certain cocycle is trivial, and the fact is that the real line has a trivial cohomology, and therefore all of the cocycles are trivial, and therefore the point is that every time you have an automorphism of a row algebra, you also get an automorphism of the compact operators, and all of the automorphism of the compact operators are inner, so you can always choose a unitary operator implementing it. But any complex multiple of this unitary operator would also do, so you have to deal with these complex multiples, right? So this result is closely related to that question.
Okay, so you are saying that in this case, when you have one parameter group of automorphism, the question about the existence of this H versus the question about being unitary implemented is the same question, but in the more general context, in which instead of the group R, you would have some different, maybe more complicated group, this question wouldn't be the same, yes?
Exactly.
Okay, thank you.
Okay, so this raises a lot of questions. The two main questions are this. Suppose we are given a self-adjoint operator on L2 of x. Okay, just any self-adjoint operator. So the first question is, when is C star U of x invariant under conjugation by those e to the ith? In other words, when is this algebra, when does H induce a preflow on C star U of x? Right? So given any operator, you can ask this question. Now, if this question is answered positively, then we can ask, when does this formula up here define a flow on C star of U? I mean, I wrote here in parentheses strongly continuous. This is, of course, redundant because flows are strongly continuous. But the question is that once this formula defines a preflow, when is this flow when is this preflow strongly continuous? So those are the two questions that we have been working with, and we have partial solutions to, and that's the main content of this talk. Okay, so now, as I said, row algebras are very closely related to this basis. So the answer, I should say that we have no answer to question A and B in full generality, because we believe that this is a very hard question. So we have been trying to study by lowering the bar and looking at special cases of this question. Right? So the first thing is that if you're talking about a flow on a uniform row algebra, we must require, in order to be able to say something, we must require them to be well behaved on the partial isometries VF. Right? The partial isometries VF are, of course, very closely related to the basis. Right? So here's a definition, which is an attempt at simplifying, at restricting flows in order for us to be able to say something. So we're going to say that a flow is a coarse flow if for every partial translation f on x, Vf is an analytic element for our flow. What's the definition of an analytic element? If you have any flow, we have just seen that the definition of strong continuity requires this function to be continuous. Right? So this function is always continuous as long as we have a flow. But we are here requiring that this function is not only continuous, but we want it to admit an extension to an entire function on the whole complex plane. Right? So in particular, this function is going to be analytic. Right? So this is our definition of a coarse flow. A coarse flow is a flow such that this function over here is very well behaved. So I should argue that this is not too strong a condition, because every flow on any C-star algebra contains a dense set of analytic elements. It's a general theorem. Every time you have a strongly continuous flow on a C-star algebra, if you look at the elements that make this function admit an entire extension, they are dense. So there's always plenty of elements to look around, to look for, and we want the flow to be so placed that those VFs are contemplated to being analytic. Another point. Okay.
I have a question. So this function is a function of a real argument.
Yes.
So if you are talking about extending this to a function on a whole plane, complex plane, then you are extending something which, of course, is analytic along this real line. But then how do you know that the maximal extension of this would be a function at all? Because usually, if, for instance, you can have an algebraic function which is defined on real numbers as a single valued function. But if you start extending this to the complex variable, it turns out that this algebraic function has a non-trivial monodromy.
Right.
So this extension is not an extension to an entire function. Its analytic extension becomes a multivalued function of a complex variable.
Right. But my definition.
How can you avoid this, knowing only about the property along this real line?
Maybe you're talking about a different definition of an entire function defined on an algebraic variety covering the complex plane. But here, my definition of an entire function is simply an analytic function defined on the complex plane. So
yes, I understand this. I understand this. But you say that this is not too strong a condition. But typically, if you have some analytic function of a real variable, usually you don't have this extension.
I understand that analytic functions.
So what guarantees us the extension of this entire extension?
Analytic functions of a real variable, they are not necessarily covered by this. I mean, they do not necessarily have an extension.
Yes.
Right. So if that's the case, if this function here behaves like what you're saying, then VF is not said to be an analytic element.
Yeah, I understand the definition. My question is about this comment. Notice that this is not too strong a condition. And we have 2 points, the first and the second. The set of analytic elements is dense, and so what is the reason? Why this extension in this class is so abundant?
Why is it
surprising? It's
for instance, why these analytic elements are dense in this context? Because
I mean, this is a theorem.
It is not. That's true. It's not true.
This is a theorem, and it's not an easy theorem to prove. And you can find it in Brettley Robinson, and it's true. I mean, there's a tricky argument using convolution products. Yeah. So it's not a
somehow that is real. The image of this real line is an orbit. Yeah.
Yes.
Okay. Thank you.
Right. So it's a striking theorem. It's a very important theorem, and the reason why I find it striking is that you start by requiring continuity, right? When you talk about a flow, you require continuity of this function, but then suddenly you get those functions which are much more regular than continuous, right? They have an analytic extension to the whole complex plane without any poles, without any monodromy, without any extension to an algebraic variety or anything like that.
So does it mean that this function can be written as a series with an infinite convergence radius?
Exactly.
Okay.
Any analytic function on the whole complex plane has that property. Yeah. And in fact, this is equivalent to what we're saying. Yeah. Mm-hmm. A good point. Yeah.
Mm-hmm.
Okay.
I have a very stupid question. Please forgive me. I'm a bit confused because one time you write H as a self-adjoint operator, and then you have the same letter, lowercase h, for a course function.
Yes.
So it's a non-commutative extension. Now H is a self-adjoint operator, which maybe is not diagonal with this.
But it was mentioned that the same notation would be used.
Okay,
Yes.
somehow I missed it. Okay, so that's a special case, right? Course function is a special case of having a self-adjoint operator, diagonal one, right? Okay, thank you.
Exactly. So if we have a course function, the definition above was that we interpret this function as an operator, and then we take this formula with the exponential. Okay, so as I said, we believe it should be very difficult to study general flows, so we will be looking at coarse flows. So our hypothesis will have coarse flow here and there. So on the one hand, we're talking about flows. On the other hand, we're talking about operators. So a similar restriction would be restricting the operators that we will look at. So in order to study unbounded operators alongside uniform algebras, we need to require our operators to be well behaved with respect to the partial isometries VF. And what do I mean by being well behaved? So let's say that H is a self-adjoint operator on L2 of X, and I'm going to say that H is a coarse operator if for every partial translation F, we have these two properties over here. Mm-hmm. So first of all, I want the domain of the operator to be invariant under my partial isometries. And secondly, I want my partial isometries to commute with H up to a bounded operator. Right? So those two properties define what I'm going to call a coarse operator.
So I have a question. Does the condition number 2 is a generalization of some kind of finite propagation property?
We're going to see that it is related to that. And I'm going to introduce a generalized notion of finite propagation, which will be related to that. Now, a few observations is that an unbounded operator is not defined everywhere. So every time you talk about composition, you may run into trouble. But one observation is that this operator here is well defined on the domain of H, right? Because you can see that if you plug in this on any element, especially over here, if you apply VF to a vector, then the outcome is in the domain of H. So this operator, this commutator here, is well defined on the domain of H. And so when we talk about the norm in item number 2, we are talking about the norm on this domain. Okay. Another observation that's crucial is that 1 implies that every basis vector lies in the domain of H. And this is equivalent to saying that C00 is a set of all sequences indexed on X with finitely many non-zero coefficients. This is always in the domain of H. It's a little bit of a computation, but 1 implies that. And again, our results will be for coarse operators most of the time. So here is our first main result, which is the solution of question B. Remember, what was question B? Question B was that assuming that a self-adjoint operator H leaves the uniform algebra invariant, when is it a flow, right? So we are taking a self-adjoint operator and we're assuming that it induces a preflow. So the following are equivalent. This preflow is actually a flow, and second, H is a coarse operator. So that's our answer to question B. Now let's turn to question A. So the question A now is, when is, right? So remember, question B was assuming that this holds, then when is it strongly continuous? Now we are asking, when does this hold? This is question A, right? So speaking about question A, we have seen that it always has a positive answer if H is diagonal. Remember that the matrix gets multiplied by coefficients, and so the matrices share positions of zero entries. So the answer is always yes, right? And we should say that a diagonal operator, even if it's unbounded, it has propagation zero. So in a certain sense, it morally belongs to C star U. So it's no surprise that this thing here holds. Now, this becomes...
Even if it's unbounded, did I hear you well?
Say it again?
Even if it's unbounded?
Yes. If even if an unbounded, every unbounded diagonal operator leaves the uniform row algebra invariant.
Yes.
Right? So the answer to question A is always yes. So
no, Piotr, I mean that this word morally here somehow explains what how should you think about it. So the only abstraction for this unbounded H but diagonal to be an element of the CU star of X is the fact that this is unbounded, but it has propagation zero. So I believe that in that sense it morally belongs to
Yeah. I just wanted to make sure I heard it correctly. So I asked about the adjective unbounded. Okay. Yeah, thank you. Yeah. Mm-hmm.
So it is very much similar to the notion of the operator affiliated with von Neumann algebra.
Yes.
Exactly.
Oh, yes.
Exactly. Yeah. That's a very good analogy, but not technically, right? Because technically, an operator is affiliated to a von Neumann algebra if its spectral projections belong to the algebra.
Mm.
But here, at least we haven't studied from that point of view. You will see what our definition of morally is. So that's the main question. In the case of okay,
assume that H is unbounded. Okay, can be then H regarded as an unbounded multiplier rather than affiliated element?
The uniform row algebra has a unit, so it doesn't have any sort of multipliers.
But this is an unbounded operator.
Yeah. So it won't be. It will never be a multiplier.
No, I'm talking about the non-bounded, unbounded multipliers.
I mean, I understand that an unbounded multiplier is an unbounded operator that multiplies every element in the algebra into itself. But if the algebra contains the unit, if the algebra contains the unit, then that will never going to happen.
Exactly.
Yes.
No way.
What about there's an idea?
Yeah, but all of those ideas, they are somehow related, right? I mean, everything we're talking about has to do with, when you look at an unbounded operator, when is it morally part of an algebra of bounded operators?
I'm trying to pin down the precise meaning of this moral.
Yeah, we are going to do that. We are going to do that.
Okay.
So, I mean, that sentence here is that we must define exactly what does it mean to say that an unbounded operator morally belongs to C star U of X.
Oh, yes, I see.
Okay, so the first question, the first point is that we have to lower the bar and speak only there's a typo here. This word bounded here should be unbounded. So first we must restrict to bounded operators whose matrix in the canonical basis of L2 has any meaning at all. So the point is that if you have an unbounded operator, then the unbounded operator has a dense domain, and there's no reason why it's defined in any of the vectors of the canonical basis, right? So if the dense domain of the operator does not have any vector of the canonical basis, then the matrix of the operator cannot even be defined, right? So this is bad because we're looking, our analysis of operators in the row algebra is strongly related to its matrix representation. So we must restrict to the unbounded operators for which the matrix has any meaning at all. So this is what we call an admissible operator. Okay. So let H be a densely defined linear operator on L2 of X. We will say that H is admissible, first of all, if it's a closed operator, if its domain contains all of C00 of X, and finally, if this formula here holds for every psi in the domain of H. Okay. So what does this formula 3 says? Let's analyze formula 3. So every vector psi has a decomposition relative to the canonical basis with coefficients psi x. So if you apply H on both sides of this formula over here, so this formula says that you are allowed to take H inside the formula, right? So H of psi is equal to the summation of the coefficient psi x times H of the basis vector. So formula 3 is saying that you are allowed to bring H inside the sum, even though the sum involves a limit, and even though the operator is not continuous, we are asking the operator to be a little bit continuous, at least so that it can be, this formula holds, right? Another consequence of this is that H can be represented as a matrix, right? In the finite dimensional case, every operator is represented by a matrix using this formula. And so for an admissible operator, the matrix representation works well. I must apologize because you know that in Brazil, you guys are making us miss our lunch. And so I am going to have a bit of a snack while we continue here.
Bon appétit.
Okay. Thank you. Okay, so this HXIs I was talking about here, they are the matrix entries of the operator H, right? Okay, so another remark.
I have a question, another question, sorry. If we assume that H has a matrix in this standard basis, what else we have to demand from this H to make this implication from the claim of the theorem to be if and only if? What is missing?
That is an interesting question. And I mean, the point is that we haven't been doing, I mean, in my whole knowledge of the field, I've never seen anybody talking about matrices of unbounded operators, right? But of course, if you have a matrix, one let's say that given a matrix, we want to define an operator from the matrix. So the first point is that you want to define the operator on the basis vectors. So the image is going to be what? The column, the corresponding column of the operator, right? So we certainly require that the columns be square summable. So let's say we have a matrix such that the columns are square summable. Okay, so that allows us to define the matrix on every vector, which is a finite linear combination of the bases. Okay, so then the operator is already defined on C00. Right? And then we want to know, can we extend this operator any further than C00? So one question is this operator closable? Right? We know that the closure of the graph of an operator might not be the graph of any function. So looking at the matrix, when is it closable? Well, I think those are very elementary questions that I don't think have ever been addressed.
And so the third condition should be understood as an equality in the Hilbert space. So the convergence on the right-hand side is convergent in L2. Am I right?
Exactly.
Okay.
Exactly.
Okay.
So this is all a very strong condition. Okay. So if we have an admissible operator, another consequence that's not so obvious is that if you have an admissible operator, then C00, which is a subset of the domain of the operator, is always a core for H. A core for H, a core for an operator is a subset of the domain such that if you restrict the operator to this subspace, and you take the closure, you get your operator back, right? So this says that the graph of the restriction is dense in the graph of the operator. All right. So if we are given an admissible operator, then we have a matrix, right? So if we have a matrix, we can talk about its propagation. So we say that an admissible operator, an admissible unbounded operator has finite propagation if the propagation is finite. Propagation is the same definition that we had before, the supremum of the distances of the entries for which the matrix entries is non-zero. Good. Now, within this definition, we are also defining what is an operator lying in the unbounded part of C star U of X. Now we have arrived at the definition of that we were talking about morally belonging to. So this means that for every epsilon, there is a finite propagation operator H prime, which is according to the definition above, such that the norm is less than epsilon. The norm, those are unbounded operators, right? So the norm could even be infinite. And I mean, there's a question of which domain you look at when you compute this norm. So you look at the intersection of the domains. So H minus H prime is an operator on the intersection of the domains. So you can define the norm here. So we require that the supremum blah, blah, blah is finite, right? And so this is the definition of an operator being in the unbounded part of C star U of X, right?
So in particular, this C00 of X always is a subset of this intersection of these two domains, yes?
Yes, because this definition here is being applied only to admissible operators. So H is supposed to have C00 in its domain, and the H prime, which pops up in here, is assumed to be a finite propagation operator So it's part of the definition that it has C00 in the domain.
Okay.
All right. Okay, so the set of all such operators we call C star U unbounded of X. Okay. So one interesting point of view is that this thing here is formed by the norm limits of unbounded operators with finite propagation. Now, there is no norm space around. I mean, unbounded operators do not have a norm, but since we are using this norm in a very specific way, we can view those operators as being the norm limits of finite propagation operators.
So again, one question. So what kind of structure does this C star U unbounded forms? Is it a star algebra, for example?
Excellent question. And we have thought about it. Our results are going to use this algebra, but we haven't really investigated. I mean, theory of algebras formed by unbounded operators, they are all very difficult. They're all very difficult. I mean, what's the structure on the algebra of operators affiliated to a von Neumann algebra?
For finite algebras, these form a star algebra, but for type 3, for example, it is no longer a star algebra.
So it's a complicated question. Yeah? So we have been trying to stay away from it, but this set, we're only looking at it as a set. This is going to have an important play an important role in here. So I can see that we are already 6 minutes over time.
No, you still have 8.5 minutes.
Oh, really? Okay.
Yes.
But in any case, we have a lot to say. So I'm going to skip property A, just to say that property A is a nice property that certain ULF spaces have, which is equivalent to the fact that C star U is a nuclear algebra. I'm also going to skip the definition of the quasi-local algebra, which has a nice picture, but let's skip all of that. And let me just say that from now on, our ULF spaces will always have property A, which you can think of as saying that we're assuming that C star U is always a nuclear algebra. Okay. So here is the our answer to question 2. When is the uniform row algebra invariant under conjugation by the exponential? So take a self-adjoint operator H, and the following are equivalent. So you will notice that course is showing up here in the hypothesis, in the conditions. Of course, we would very much like to get rid of this part of the hypothesis, but course, we cannot say much about operators beyond the course realm. So condition 1 says that H is coarse, and question A is answered yes, right? Condition B says that H is coarse, and H is morally an element of our algebra. Right? So as we have already anticipated or expected when we discussed about diagonal operators morally belonging to the uniform algebra, that's the only obstruction. So in the course realm, question A is answered affirmatively exactly when the operator is in the unbounded part of our algebra. And there's an extra condition which says that this situation here, question A, is answered affirmatively, even only if H is the sum D plus A, where D is a coarse self-adjoint diagonal operator, of which we know everything about, and A is an actual element of our C-star algebra, a self-adjoint element. So all of this is under property A, and the proof of this result is somewhat delicate, and it's based on a paper by Lawrence and Willett, which discusses bounded derivations on uniform row algebras, and we adapt their machinery in our situation here. So the grand conclusion, putting the answers together, is that the coarse flows are precisely the ones of the form of this conjugation form, where H is an operator of this form. So we have been able to fully classify all coarse flows on the uniform row algebra in the under property A. So
this is still, this grand conclusion is still under the assumption that you have property A, right?
Yes, exactly.
Okay.
As I said here, from now on,
yeah,
all of our US spaces have property A. So
I have a question to this condition number 3 about this decomposition of H into the sum of D plus A.
Okay.
If coarse self-adjoint diagonal operator is self-adjoint, what is the meaning of this decomposition if this A is simply self-adjoint? Because all elements of type D are elements of type A. Maybe I don't understand this self-adjointness of this D.
No,
D is possibly unbounded.
Exactly, it's unbounded.
Ah, so this is more okay.
Okay. You are saying that you are.
So this operator on L2.
Yeah.
Outside this. Okay.
My intuition is that you are saying, so you have this property if you just take an element in your row algebra, but uniform row algebra, but you deviate it from this just by going unbounded, but only in this coarse diagonal way.
Yeah. Exactly. Yeah. I mean, maybe I should have emphasized here, but this guy is possibly unbounded.
Yeah.
Okay, so this here, I think it's an excellent stopping point. How am I doing in time?
Well, you have 2 minutes 20 seconds left.
Yeah, so that's an excellent time to stop and maybe answer further questions.
Okay.
But I mean, there are other things that I could talk about, the KMS states. And also this other part here, which is co-cycle equivalence of flows, but that's another long story.
Okay, so muito obrigado. Let's thank our speaker. Thank you so much.
Thank you very, very much.
Okay, so any questions from anybody? Okay, let's go ahead.
So continuing about this condition number 3, I wonder what is the intersection of elements of type D and elements of type A? So it's only boundedness. So the intersection is coarse self-adjoint diagonal bounded operators.
That's L infinity.
So this is the only non-uniqueness of this decomposition.
No, Thomas, but I think that being diagonal is stronger than being of finite propagation. So
yes,
yeah,
finite propagation is like a thick diagonal, yes, in some sense.
Exactly. Yes. Yeah, that's zero propagation. Right?
So the intersection of these two classes is they are coarse self-adjoint diagonal bounded operators.
Yes. So this is L infinity.
So my question is, if bounded operators being morally elements of C star U, are they elements of C star U?
I'm lost. I don't know.
Okay, assume that we have an element which is morally in CU.
Okay.
Okay?
Okay.
And assume that it is bounded.
Uh-huh.
Then necessarily an element of CU.
Okay, now I understand the question.
Yes, yes,
Yes.
yes,
Okay.
yes.
So the intersection of these two classes of type D and type A is they are called self-adjoint diagonal bounded operators.
Yeah, and this is precisely L infinity.
So this is precisely the non-uniqueness of this decomposition of
Exactly. Yeah. So you can change one pair dA by adding an L infinity element and an L infinity diagonal to D and subtracting it from A.
Mm-hmm.
That's the only non-uniqueness that you get.
So they are simply functions. These diagonal entries, it's a function.
Exactly. Yeah. Precisely.
So in a sense, non-uniqueness of this decomposition is related to the quotient of these flows. Modulo these flows generated by these coarse functions.
Exactly. Yeah.
So in fact, we are talking about some invariant of this situation, which is in this, maybe it's not a quotient. Yes, it's a quotient group. No,
Yeah,
it's not a group. It's not a group. Sorry, it's my bad. So it's a quotient of all flows by these diagonal flows. So this could be quite complicated space. So it's not a good invariant. It's a very big thing.
Sure.
Okay, anybody else?
Adam, yes. I have a question, if I could. Since I saw bounded commutators, so immediately my association is the spectral triples. So is there any connection with the theory of spectral triples? And
I thought about it as well, but in the case of the spectral triple, we I don't know. I mean, maybe you can make a spectral triple out of one of those admissible operators, but we haven't looked at it in that direction.
And Adam, you like to have H as a Dirac operator or what?
so some choice of H would be a kind of a Dirac, this unbounded, yes?
But it wouldn't be spectral triple in the usual sense. It would be this coarse spectral triple. Of course.
Huh.
Okay, anybody else?
I have still one more question about this KMS states.
Oh yes, omitted.
So state your question.
But I don't know precisely the topic of my question, since I don't see slides. There was some remark about the cardinality of all extremal KMS states.
This is below here.
And I was very surprised to see 2 to the power 2 to the Aleph 0. Yeah.
Yes.
Exactly.
That's very surprising. Okay, so this question, this slide was about looking at KMS states for diagonal coarse flows. Right? We have a paper which is about to be published in this new journal of the Canadian Mathematical Society, the Communications, with Bruno Braga, and so we study KMS states only for coarse diagonal flows, right? But now, with this result that we just obtained, this study about diagonal flows passes to general course flows because we know that any course flow is co-cycle equivalent to a diagonal flow. So in that paper, we study KMS states, and we specifically look at one example when X is the n branching tree, right? So look at a tree in which every vertex branches into n branches, right? So this is a graph, and every graph with uniformly incidence index gives a ULF space. So this is what X is, and we choose our course function to be the distance to the root of the tree. So this gives a flow on that uniform row algebra, and we computed the KMS states, right? Computed in terms, I should say. So the solution is that if the inverse temperature is less than log of n being the number of branches, then there are no KMS states, right? This is Hawk's temperature. For beta bigger than the critical temperature log n, there's a unique KMS state, and that KMS state turns out to extend to the whole of B of H, giving a normal state, and it turns out to be precisely the Gibbs states.
Yes.
But then at the critical temperature, there's something incredibly intriguing that we get 2 to the 2 to LF0 extreme KMS states.
Wow.
So that's a behavior that people in quantum statistical mechanics have not seen so far, because normally those weird phase transitions, they correspond to a critical temperature which is approached, in which KMS states, unique KMS states are approached by multiple KMS states, but the fact that unique KMS states somehow go to so many KMS states at the critical temperature is something that I believe have not been witnessed so far in models of this kind.
Yeah, I'm also very much confused. So usually the situation is as follows, that for large beta, you have many KMS states, but for low beta, beta is like an inverse temperature, yes?
Exactly.
So small beta corresponds to hot situation and one KMS state. Kind of chaos.
So here, I mean, the system has no stability in when it's hot.
Huh.
Right. Now, when it's cold, it has only one KMS state, and as you start heating up the system, this stability point then suddenly branches into this incredible number of states.
In usual situation, one more question. In usual situation, you have only two regions, and for one, you have a strict inequality, strong inequality, like strictly smaller than something, and then you have the other inequality together with equality. Yes, only two regions, and here you have three. Yes, so this is also unusual. Yes.
Yes. Mm-hmm.
Very strange.
This, I mean, the paper is already in the archive, and it's soon going to appear in the Canadian Mass Communications if you're interested.
Okay.
And when you say that n is an integer, you mean it's a positive integer, right?
Exactly. Yeah.
Adam, are you happy now?
Yes, yes, yes. I'm happy, puzzled, and confused, but happy after all.
Wow. All at once.
All at once, yeah.
So much happiness at once.
Thank you very much.
Thank you.
Anybody else?
Yes, I have a question about this theorem. It's a beautiful theorem. But Gibbs disappeared somehow.
Okay.
So let me come back to Gibbs. So this Gibbs situation is about this partition of energies. Okay, it's like, but with this partition of energy, you can associate entropy of the situation. When I'm looking at this logarithm of this multiplicity of this branching, okay, I cannot resist to think about some microstate which could be distributed along this tree, and so maybe the right hand side relates this beta, this temperature, not to the energy but to entropy of these Gibbs states. Okay, and then I would like to understand purely because entropy is a combinatorial invariant of some partition. Okay, so I would like to understand this entropy of this situation in terms of the combinatorics of this n-branching tree.
Me too.
You have a Gibbs state, you have this distribution, probability distribution, okay?
Yeah.
And you can compute the entropy of this. And this entropy then is related to this logarithm of n. Yeah. Okay, so normalized this partition. Okay. So if you take the entropy of these, then you have something which is related to this logarithm or something. So this branching here plays a role of something which measures the number of microstates. Because the Gibbs state is a state of thermodynamical equilibrium. Okay? And it is in the state of equilibrium, the logarithm of microstates is precisely this entropy. Okay, so I cannot resist to interpret the right-hand side, this bound from the right-hand side, as kind of entropy, maybe up to some normalization. Okay,
that would be
yeah. So this critical value of this being related to the branching of this tree means that something important happens on this tree with respect to the combinatorics of this tree. But I cannot pin down what is this about. I have very sparse understanding of parts of this. Well, I know from thermodynamics, from combinatorics, from different branches of mathematics.
I mean,
I would like to understand this on the deeper level.
Yeah, I mean, there is a very another surprising aspect of this is that I wonder if I can find some open space here to write. But you know, the row algebra contains a copy of the compacts. And
is that ideal or a subalgebra?
It's an ideal. It's an ideal. Yep. And so there is another algebra which is also important to look at, which is u of x, which is the quotient, right? It's a version of the calculus algebra for the row algebra. And the Gibbs states, since they are strongly continuous, they are all supported on the compact operators. But then, as you hit up the system, they all move away, and they vanish on the compact operator. So they are actually states of this quotient algebra. So all of those states are actually states on this quotient algebra, which is also very much studied in the theory of row algebras. This is called the row corona.
Tom, are you happy now?
I have another question about this precisely. So if you have this critical temperature, inverse temperature, okay, is how to say, phase transition related somehow to the index map associated with the situation of the quotient?
I don't know. I mean, the index map in K-theory?
Yes.
I don't know. No idea.
Okay, anybody else?
May I have another question?
Please let it be.
Okay, the last one from me. KMS state is related to analyticity property on a strip. Okay?
Right.
Is analyticity on the strip somehow related to this entire extension of something? As a function?
Exactly. Because I mean, when we study KMS states, every time you study KMS states, you're interested in. I mean, the very KMS condition involves analytic elements, right?
Yeah.
So if our flows are coarse, then the VFs are analytic elements. So you can look at the KMS condition, plugging in the VFs in the KMS condition. So that's the relation. That's how we get a handle to deal with the KMS. Yeah. I mean, here's another point of view, which is interesting, is that I mean, as I said, the row algebra contains a copy of L infinity, right? So L infinity is contained in the row algebra, and there exists a conditional expectation from the row algebra to L infinity, which is simply taking an operator and erasing all of the non-diagonal entries, right? So this we call this is a conditional expectation that's very important. Now, in every situation, even in a general row algebra, we prove that every KMS state for a diagonal flow is necessarily factors through this conditional expectation. So it's actually a state here to the complex numbers, right? So every KMS state is of the form E composed with some state on L infinity. And as we know, states on L infinity are the same as probability measures on the Stone-Check compactification. So this is very much a study of measures on the Stone-Check compactification, right? And the statement that I was just making, that the Gibbs states live on K and the other ones live on the quotient, could be made, could be rephrased if you look at the Stonechek compactification of X, which is the spectrum of L infinity, it of course contains X. So the Gibbs measures, they are supported on X. And all of the other weird states, they are supported on the boundary, which means the complement of X within the Stonechek compactification. So that's a very delicate problem because, you know, in order to exhibit a single point in beta of X, which is not in X, you require the axiom of choice. And so in order to deal with measures on that space, you are really walking on thin ice.
Okay. Anybody else? Gilles, Ali, Yang?
Yes. I just have a small questions about the embedding of infinity in the row algebra. My question is that yes, my question is that is it a trivial question that what is the idealizer of the L infinity in the row algebra?
So L infinity is a Cartan subalgebra.
Sorry.
So you're talking about idealizer. What exactly do you mean by idealizer?
Idealizer, I mean that all assume that A is a subalgebra of B. Then the idealizer of A, it is possible. The idealizer of A is all elements whose commutator with elements of A belongs to A.
Okay, I see. I mean,
something similar to the concept of normalizer of subgroups of given groups. So I wonder. Yes.
Okay, go ahead.
Yes. I wonder. I do that L infinity is an ideal in the row algebra. Yes.
No, because L infinity is unitary.
Compact operators are ideal.
Sorry?
Compacts form an ideal in row algebra, not L infinity.
L infinity is a commutative subalgebra.
Yeah.
It's not an ideal.
Yes, L infinity is commutative, but row algebra is not a unitary algebra, no?
Yes, it is. It is. I mean, the identity function is
okay.
A partial,
so my question is that yes. So my question is that what is the idealizer algebra of L infinity in the row algebra?
I think it's itself.
Is it
trivial?
trivial?
I think it's just L infinity.
Mm-hmm.
Yeah. I mean, I think it's just. I mean, what's very interesting is what are the normalizers?
Yes.
Right.
Yes, my question was stupid because the inclusion is a unitary inclusion. Yes.
Exactly. Yeah. But normalizers, I mean, this is a very interesting question because L infinity, as I said, is the Cartan subalgebra of the row algebra. So it has many normalizers. And in fact, saying that L infinity is a Cartan subalgebra involves saying that the normalizers. So that normalizers span the row algebra. So there are lots of normalizers. So among the normalizers, you have the VFs. All of the VFs are normalizers of L infinity, right? And I mean, having a Cartan subalgebra means that C star U of X is a groupoid C star algebra, right? So it's a groupoid C star algebra for an tau groupoid, for an ample groupoid.
Yes. Okay. Thank you.
Okay, great. So I think it is time to wind it up, right? So let us obrigado our speaker one more time for a very beautiful talk. Thank you so much.
Thank you.
Thank you. Thank you very much.
Let me stop recording, but please don't go away.